the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is yet another video in a series on orthogonal sets, specifically on an introduction to orthogonal projections. Now, it is important that you've already watched my video or have studied orthogonal bases because we're going to use that topic here. Specifically, we're going to use this formula that you can see right here, where we had been given an orthogonal basis for a space and a vector y from that space that we wanted to write in terms of the orthogonal basis vectors. And we proved that the coefficients of that linear combination of orthogonal vectors ended up being just this formula right here. The jth coefficient of the orthogonal basis vectors is the fraction where the numerator is the dot product of the vector in question with the jth orthogonal basis vector, and the denominator is the dot product of that jth orthogonal basis vector with itself. Now, like I said, that's going to be very important for this conversation here. So if you are not comfortable with that, please go back and watch my previous video in this series. But for now, we're going to jump right into orthogonal projections. And just to give you an idea of where we're driving this conversation, we would like to build orthogonal bases for a space. And that's what we're deriving as we move forward here. So let's begin with a theorem. Suppose that W is a subspace of the vector space V and that Y is just a vector in V. So again, we're really focusing on W being a subspace of the vector space V, but Y is not necessarily in W. Y is in V. It could be in W, but let's go ahead and just say it's in V only. Then Y can be written as the sum of two projections. The projection of Y onto the subspace W and the projection of Y onto the subspace W perp, where, as I just said out loud, this notation is called the projection of Y onto the subspace W, although officially it's called the orthogonal projection of Y onto W. And the projection of Y onto W perp is a vector in W perp called the component of Y orthogonal to W. It's important that we take the time to define what these notations are, because this is probably new to you. The projection of Y onto W and the projection of Y onto W perp. These are actually just vectors. The first one is just the orthogonal projection of Y onto the subspace W. The second one is really Y projected onto W perp. That actually has a name, so let's go ahead and zoom out and see these things. The projection of Y onto W is a vector in W called the orthogonal projection of Y on W. And the projection of Y onto W perp right here is again a vector, but this time in W perp. And it's called the component of Y orthogonal to W. Now, if that seems somewhat confusing, help is on the way, because we're going to visualize this in R squared because it's just easier to visualize it in R squared. So as I say down here, rather than a proof, which right now with my language that I'm using is quite impossible, let's do a visualization. We will be able to prove something more important than this in a moment, but what I really wanted to do with this language version of the theorem is to give you a basic idea of what's going on. Now, before I begin with this, I should mention the subspace W is usually the span of a vector or a group of vectors. So let's pretend as though somebody's come into the room here and said, hey, I've got a vector, let's call it U, and we'll create the span of that vector, which we know is a subspace. So there's the vector U right now. And what I'm going to do is go ahead and showcase the span of that vector U. There we go. That blue line is the span of the vector U. I'll actually write that in there, which we're going to call W. So that line in R squared here is just going to represent the subspace spanned by the vector, the single little vector there. Now somebody comes in the room and says, great, I see that you've taken that vector U and you've drawn out the span of that vector, but that's not the vector I wanted you to work with. Sorry about that. I want you to work with this vector now that I call Y. and they hand it to you like that. There is the vector y. And they say, well, guess what? I could technically decompose that y into the sum or a linear combination of the standard basis vectors for r squared. It is totally true. I could totally do that, but I don't want to. I actually want to write that vector y in terms of the vector u and a vector orthogonal to u. So again, instead of referencing everything from the standard XY coordinate system or Cartesian coordinate system and saying, oh, go to the right so many units and go up so many units to get to the tip of Y, we instead are going to change our perspective and look at the world in terms of this tilted view. This is a right angle right there. So these axes are orthogonal to one another. They've just been tilted. And one axis is on the subspace W. The other axis will be perpendicular to that subspace W. Hence the language that I'm using up here. We're going to project Y onto the subspace W and also project Y onto the subspace W perp. In the end, you get these two vectors, one in red, which is called the projection of Y onto W. It's called the orthogonal projection, really, because that's what we're doing, is an orthogonal projection of Y onto W. And then the green vector is called the component of Y orthogonal to W. Or you could just call it the projection of Y onto W perp, whichever you want to call it. It's actually the same. Now, something I want you to see from this is that if we took a look at the red vector here and the green vector, we could move that green vector right here, and you could see from tail to tip addition that the red vector plus the green vector is actually what Y is. So therefore, Y is definitely the sum of the projection of Y onto W and the projection of Y onto W perp. Now that visual is not a proof, but it is a really nice visual for what we're going to be doing. We essentially just want to break a given vector into two or more component vectors that are orthogonal to each other. Now, to be honest, that last theorem is really great for conceptualization, but it's not that great if we can't actually compute those projections. We need a way to compute what those projection vectors are. In future lectures, we'll want to decompose a given vector into a linear combination of the orthogonal basis of the space. For now, let's concern ourselves with projecting a vector onto the subspace spanned by another linearly independent vector. So let's figure out, or at least work with a theorem that allows us to find what that projection vector is. So suppose that W is a subspace of a vector space V. Further, let's suppose that W is the span of a vector U. Now notice I'm doing this only in terms of the span of a single vector. So for right now, for this conversation, W is just a single dimensional subspace. We're also going to assume that Y is a vector in V, which W is contained within, right? Just Y does not have to be actually on the subspace W. Again, a great visual for that is right here. We have our subspace W right here. We have our vector Y, which is not actually on that subspace. It's in the vector space V. It's not on the subspace W. Well, it is at 0, 0, but that's about it. Now, to be honest with you, I'll probably go back and forth between that picture and this proof as we go through, because that's going to help quite a bit as we go through this. Anyway, so if all of that stuff is true, that we have W being a subspace of a vector space V, and that W is just a span of a single vector U, and that Y is in the vector space V, then the projection of Y onto the subspace W, or what we would call the orthogonal projection of Y onto W, is Y dotted with U divided by the magnitude of U squared, then times the vector U. Now I'm going to pause before we continue because I want to show you that we've seen this already. So in theorem 5 from the last video, we said that somebody could come in the room, hand us a vector Y, and if we have an orthogonal set of vectors, specifically an orthogonal set of basis vectors for our subspace W of Rn, then we should be able to write Y as a linear combination of that orthogonal basis. And we made a claim and we proved it that the linear combination, or the weights of the linear combination, were given by this fraction right here, which by the way is just y dotted with u sub j over the magnitude of u sub j squared. Well, if that's the jth coefficient of this linear combination, then that linear combination could be rewritten as what you see in the colorful yellow and blue down below. Now just focus for a moment on only one of those, and you will see that's exactly what our current theorem is stating. So we're reducing our n-dimensional space that we were working on in this specific, I guess it's p-dimensional for the subspace, but we're reducing that down to a single dimension for the theorem that we're working on, and then we'll grow that. So all we're going to work on right now is just saying, hey, guess what? I could write y as y dotted with u over the magnitude of u squared times the vector u. And that's what you see right here. That's going to be called our orthogonal projection of y onto w. So let's start the proof. It's important to note here that w is being represented as a line in r squared. However, this is only done for visualization purposes. And again, I will go ahead and use the line we already drew in the previous page to help us out. In fact, let's hop over there just to refamiliarize ourselves with that line. Now, just by this drawing, we can see that the projection of y, the orthogonal projection of y onto w here, is some scalar multiple of u. It doesn't have to be a large scalar multiple of u. It could actually be smaller. Like this red vector could have been smaller than or shorter than the vector u if the vector y was shorter. So just the punchline here is that this projection of y onto the subspace w is some constant times u. I'm using k on purpose here because we always use c. And for simplicity, for this proof, I'm going to go ahead and not use that language right there. I'm just going to call that vector v. So we have u and we have v. They're orthogonal to one another. U is called the orthogonal projection of y onto w, and v we're going to call the component of y orthogonal to w. So making little notes here, we can see that the projection, orthogonal projection of y onto w, is just a multiple of u, and we're letting v be the projection of y onto a vector orthogonal to u. Now, something we should have noticed from that previous page, and something that I had mentioned just a moment ago, but this time I'm going to actually write it down. The projection, or the orthogonal projection of y onto w plus the vector v should be y. In other words, that red vector plus the green vector should be y. Again, to help you visualize that, here it is, right? So the red vector plus that green vector definitely lands at the tip of y. And that's what I state right here. Notice that the projection of y onto w plus v is equal to y. The red vector plus the green vector is equal to the black vector y. Now, doing a little bit of algebra and subtracting the orthogonal projection of y on w from both sides, we get that v is equal to y minus the projection of y onto w. But since v is orthogonal to u, we know that if we take the dot product of v and u, that dot product should be 0. And if that dot product is 0, well, there's another way to write that dot product. We happen to know what v is. V is this guy right here. So what I'm going to do is trade out that v in that dot product for y minus the orthogonal projection of y onto w. There we go. And now I'll do a little distribution, and that's just from the properties of dot products. But we had mentioned something about the projection, the orthogonal projection of y onto w. We had said that that's just a scalar multiple of u. Again, before I do the big reveal here, I want to just convince you of that. So remember, the red vector is the orthogonal projection of y onto w. U is actually hidden underneath this. It's right here. So that red vector is actually just a multiple of u, a scalar multiple of u. So wherever I see that orthogonal projection of y on w, I could replace it with just some scalar multiple of u. And that's what I'm going to do right here. So now we have y dot u minus, instead of the projection of y on w dotted with u, we have k u dotted with u. And so you could see 0 is supposed to equal that. So if I decided to add k u dot u to both sides and then divide by u dot u, we would get this statement right here. That constant k has to be this fraction. So we're going to take that and we're going to sub it back into the orthogonal projection of y onto w. Remember, that's supposed to be k times u. And when we do that, we get the following. The orthogonal projection of y onto w is just k, which we've just discovered is y dotted with u over u dotted with u. And then remember, that's just k. We still have to multiply by the vector u. And by the way, that denominator u dot u is just the magnitude of u squared. And there we have proven it. That's actually not too bad. And by the way, that last line is actually called the orthogonal projection of y onto u, even though it's actually onto a scalar multiple of u, to be very honest with you. So let's use this in an example. Compute the orthogonal projection of y, this vector y right here, onto the line going through the origin and this vector v right there. Now you could visualize this if you want to. There I've drawn in black the vector y and in red the vector v, and I want to compute the orthogonal projection of y onto the line going through v. In other words, onto the scalar, the subspace spanned by the vector v. Now if I've drawn that appropriately, which I think I actually have, then visually that green vector right there should be the orthogonal projection of y onto the subspace spanned by v. That's probably how I refer to it from this point forward. So let's do our work here. Now I'm going to start with this statement that I'm taking the orthogonal projection of y onto w. W is a subspace spanned by the vector v. Notationally, that's how we would often write it, so we might as well just stick with that. And the formula is simply this guy right here. Again, you could write that denominator as the magnitude of v being squared. The reality is, it's probably just easier to dot v with itself. And I mentioned it in the last video, but I just want to repeat it here. When you're dealing with dot products, you cannot cancel factors. These are not factors. So you cannot just say, oh, that v cancels with that v. That's illegal. Likewise, you cannot say, well, I'll cancel this v downstairs with this v out back. That is not how mathematics works, at least vector mathematics. So just do the actual dot products. So y dot v is going to be -6 plus 2, or -4. And v dot v is 4 plus 4, or 8. And then we have times the vector v itself. That's -1/2 times -2, -2, which is the vector 1, 1. Now, if I had plotted coordinates here, and if I measured everything out appropriately, which I kind of did, you could see this is over 1. This will actually be up 1. This is definitely the point 1, 1. So that does work out. Our mathematics matches our geometry. That's really pretty. That's very nice. So there you go. Very fast, right? There's nothing really to it. But this formula for computing the orthogonal projection of a vector onto a subspace is going to haunt us for quite some time. So get used to it. It is one of those that you have to commit to memory. Now I include this example because of the fact that it's going to end up being important for something we learn in a few lectures. Being able to write a vector as the sum of a couple other vectors, one being from the span of v, which is basically what we just found. We found a vector in the span of v, which is called the orthogonal projection of y onto w, or the space spanned by v. So we want to write this vector y as the sum of that orthogonal projection and a vector orthogonal to that projection, essentially. And to do this, I'm going to derive the sum using our geometry from the last picture. So looking back at our previous geometry here, notice that we have the vector, which is the green vector here. This is the projection, the orthogonal projection of y onto the subspace spanned by v. And that should make sense. There's the black vector y right there. If you cast its shadow onto the subspace spanned by v, it is that green vector. Likewise, we can cast a shadow on the subspace orthogonal to that, and that shadow would actually be this blue vector. And remember, that blue vector is called the component of y orthogonal to w. So you can kind of think of the green vector as the component of y on w, and then the blue vector as the component of y orthogonal to w, if you want to think of it that way, I suppose. But one thing you should note here is the sum of those two vectors is the black vector y. Again, just doing tail to tip addition, you can see the sum of those two vectors definitely is y. So it's really helpful to write that down, because what we're going to do is we're going to find out what that projection of y onto w perp is as a vector. We know what y is. It's just that vector right there, 3, -1. And we've just computed what the orthogonal projection of y onto w is. We computed that to be 1, 1. And you can see finding the orthogonal projection of y onto w perp, or in other words, the component of y orthogonal to w, is just a subtraction problem. Subtract 1, 1 from both sides, and we get down to this bad boy right here. So when they say write y as the sum of a vector in the span of v, which is just going to be the vector that is equal to the orthogonal projection of y onto w, and then a vector orthogonal to v, that's going to be this vector we just found. So therefore y must be 1, 1 plus 2, -2. Again, 1, 1 is the orthogonal projection of y onto w, and 2, -2 you can think of as the orthogonal projection of y onto w perp. That's really what it is. This skill, while not very useful right now, is going to be plenty useful in a little bit, specifically when we get to something called the Gram-Schmidt process. But we have a little bit of time before we get to that process, so let's go ahead and move forward to the very last problem in this video. Compute the distance from the vector y to the line through v and the origin. Now again, I'm going to go back to our drawing to really showcase what this looks like. I want to compute the distance between the vector y and that pink line, the span of v there. Now this is an introduction to a later topic called least squares. You're trying to find the shortest distance between 2 points, essentially. And you can see that distance between the vector y, and when we say the vector y, we really mean the tip of that vector. So the distance between the tip of that vector and the closest point to that tip that's on the span of v is going to be this distance right here. And that distance is the same as this distance right here, which is the length of the vector, which is the orthogonal projection of y onto w perp. Well, let's recall what that projection of y onto w perp is. From the previous problem, it's this guy right here. Projection of y onto w perp is 2, -2. We just need to find out what is the length of that vector, or the norm of that vector. And that's going to be 2√2. That is the distance from y to the span of v, which I'm abusing the distance notation here because normally you don't write it this way. You talk about this notation is kind of reserved for the distance between vectors, but I'm saying the distance between the vector y and this subspace generated by our vector v. Now I want to summarize here, and I think this picture is probably best for the summary. So somebody comes in the room and they hand you a vector y, and they hand you a measuring stick basically, which is how they're going to create their orthogonal space. They're saying, well, I have this vector y I want to write in terms of this vector v, sort of. I'd like it to be represented by orthogonal vectors, it being y. I need y to be represented by two vectors that are orthogonal to each other. One of those vectors will be on the span of v, and the other vector will be orthogonal to that span. So the vector that's on the span of v is the green vector. The vector that's orthogonal to that is the blue vector. Y can be written as a sum of those two vectors. We now know how to find the orthogonal projection of y onto the subspace spanned by v. That's just going to be y dot v divided by v dot v times the vector v itself. And we know how to find the projection of y onto w perp because y is just the sum of those green and blue vectors. And so the projection of y onto w perp is going to be y minus the projection of y onto w. All right, that does it for this video. I hope that you found some of this information, hopefully all of it, useful, and I hope to see you in future videos. Have a great day. Be a wonderful human being.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.